So we've been talking a lot about solids and liquids and how intermolecular forces play a factor in whether something will be solid, liquid, or gas. So this is a great opportunity for us to revisit phase changes. As you may recall, a phase change is simply when matter changes from one state to another, such as solid to liquid or liquid to gas. In topic 1, we briefly covered this, and so we're going to revisit by categorizing the states of matter, or the phases of matter, into two different categories, 3 phase changes under each. So there are 6 phase changes altogether. There's melting, vaporization, sublimation, freezing, condensation, deposition. These 6 phase changes can be categorized into 2 main umbrellas. The first one are what we call endothermic, which means heat needs to enter in order for these particular phase changes to happen. So for example, if you want to melt something, let me use the highlighter. If you want to melt something, that requires you to add energy, to add heat. And hopefully you're all familiar with that. That's going from a solid to a liquid. The temperature at which something melts is known as the melting point. If you want a substance to vaporize, which means going from liquid to gas, that needs to require heat as well. This is going to happen at the boiling point. And finally, it is possible to actually have something go directly from solid to gas. This is known as sublimation. There's no such thing as a sublimation point. We don't talk about that. But these 3 phase changes are what require heat. Heat needs to go in. The other 3 are exothermic, which means heat needs to leave. Heat needs to get out of the particular system. And so for something to freeze, which is going from liquid to solid, that needs to release energy. This is known as the freezing point. It is actually important to know that the melting point and freezing point for a substance is exactly the same. What temperature does water melt at? 0 degrees Celsius. What temperature does water freeze at? 0 degrees Celsius. It's the same temperature. It's just its opposite directions. So if I'm freezing something, if I was freezing water, I would say, oh, the freezing point of water is 0 degrees Celsius. If I was melting it, I'd say its melting point is 0 degrees Celsius. But it is actually the same temperature. If I want to condense something, that means I want to take it from the gas to the liquid. We actually don't have a condensation point. I'm not sure. I don't know why we have a freezing point but not a condensation point. It doesn't make sense to me. So we don't have that. But that's the phase change there. And then finally, deposition, going directly from gas to solid. The sublimation and deposition ones might be difficult for students because, that kind of seems weird, right? You can go directly from solid to gas or gas to solid. An example of sublimation would be solid carbon dioxide going directly to gas carbon dioxide, which you might not be familiar with that, but solid carbon dioxide is actually dry ice. So when you get dry ice in that block and you put it out and it goes directly into the gas phase, that you are witnessing sublimation. And that obviously can be reversed as well. You can take solid carbon dioxide, or gaseous carbon dioxide, and bring it down to a solid. And that's known as deposition. Now, when you heat a substance up, so for example, you take this solid and over time, you increase the temperature. The temperature is going to increase, but notice it reaches a point where it levels out. The leveling out is the actual phase change. You are now melting it. During a phase change, temperature does not increase. It actually stays the same. So what is happening during a phase change? For example, if you're heating something and you're adding all this energy because of the flame, but it's not increasing the temperature, what is that extra energy doing? Well, for something to go from a solid to a liquid, all of the intermolecular forces have to be weakened. So during a phase change, specifically with melting, intermolecular forces have to be weakened. Once they're all weakened and it's now fully in the liquid phase, the temperature will increase again until it reaches the next phase change, which is vaporizing or boiling. Make sure you say vaporizing, not boiling, because it should be vaporization. Once again, right there, intermolecular forces this time actually need to be broken. And notice it's broken because once you get into the gas phase, there are no intermolecular forces. They're gone, right? So at that point, once the intermolecular forces are all broken, you'll be fully in the gas phase and the temperature will increase as well. Now, if you were thinking about the opposite, if you wanted to take a gas and cool it down to a liquid and then finally freeze it to a solid, same thing. Okay, decrease your temperature. When condensing is happening, the temperature will not change until it turns into a liquid, and then it will continue to go down until it goes through the freezing process, and then it will go down as well. So the key thing to note is that during a phase change, temperature does not change. And that's because the intermolecular forces are being either weakened or broken or reformed in the case of cooling. Now we can actually quantify this, and we haven't done some calculations in a while, so this will be a good opportunity for us to get back into the swing of things. We can quantify this by what's known as heat of fusion and heat of vaporization, which have these symbols over here. We'll talk more in topic 12 about this whole delta H symbol, but for right now, just think of it as heat. Now you've got fusion, which has the sub FUS, and then vaporization. When you hear fusion, I want you to think of melting. It's the same thing. So fusion is the same as melting. So what is a heat of fusion? It is the amount of energy needed to melt 1 mole of a particular substance. Every compound has its own heat of fusion, and it also has its own heat of vaporization. You can look these values up in the back of a textbook or online. So if I were to look up water's heat of fusion, I would get 6.01 kilojoules per mole. What that means is it takes 6.01 kilojoules of energy to melt 1 mole of water. Heat of vaporization is very similar, but it's the amount of energy needed to vaporize 1 mole of a substance. If I were to look up water in the back of a textbook, the heat of vaporization would be about 40.67 kilojoules per mole. In other words, it takes 40.67 kilojoules to fully vaporize 1 mole of water. Now you notice the vaporization value is much larger than the fusion value. That's always going to be the case. The heat of vaporization is always larger, and that's because when you melt something, when you take something from solid to liquid, all you're doing is weakening the intermolecular forces. But when you take something from liquid to gas, you're breaking all the intermolecular forces. That takes more energy to do. And that's why the heat of vaporization will always be larger than the heat of fusion. Now you notice there's no heat of freezing. There's no heat of condensation. And that's because, well, it's just the opposite. So if you have to add 6.01 kilojoules to melt something, then that means you would have to remove 6.01 kilojoules per mole to freeze it. And if I have to add 40.67, I would have to remove 40.67 to condense it. So you just reverse the sign if you want to know how much energy needs to be removed to freeze or condense. And like I said, every substance has its own heat of fusion and heat of vaporization. I've provided a table that have 6 compounds, their formulas, and then their heat of fusion and heat of vaporization values. I would give you this information on an exam, so you don't have to memorize any of this. But let's take a look at some examples of how you would solve these types of problems. So let's take a look at example 7. If you have 15.0 grams of ice at 0 degrees Celsius, so that's at its melting point, it's ready to go, how much energy is required to melt it? So I'm starting off in grams, and I need to somehow get it to the amount of energy, which is kilojoules. Well, we can't go directly from grams to kilojoules. We have to first go into moles first. So a little review on mole conversions. I know it's been a while. So the first thing I'm going to do is I'm going to take this 15.0 grams of ice, which remember, ice is just water. It's just solid water. And I'm going to convert it from grams of H2O to moles of H2O. So 1 mole of water is going to have a molar mass of 18.02 grams. So the grams will cancel, and now I'm in moles. And then the next thing is this is where I go from moles of water to my energy. Now, this is where I'm going to use my delta H. I just have to figure out what delta H do I need to use. Well, we're melting, so that's going to be my heat of fusion. And specifically, let's find water. It's 6.01. So for every 1 mole of water that I have, it will take positive 6.01 kilojoules to melt it. So the moles will cancel, and now I'm going to go ahead and be in kilojoules. So let's calculate that out. All right, if I do 15.0 times 6.01 and then divide it by 18.02 with 3 sig figs, I end up getting 5.02 0.00 kilojoules of energy. That is what would be the amount of energy I would need. Now let's take a look at example 8. In example 8, we're actually going the opposite direction. So it says if 2.45 kilojoules of energy are released when benzene is condensed, how many grams of benzene do you have? So this time we're starting with kilojoules, and we want to go to grams. Same thing, we still need to go through moles first. So same idea, just opposite direction. Now notice it says if 2.45 kilojoules of energy are released. So mathematically speaking, that means I need to write out negative 2.45. So make sure you do that. Negative 2.45 kilojoules. It's because it's released. Now the first thing I'm going to do is I'm going to go from kilojoules to moles of benzene, which is C6H6. So for every 1 mole of benzene, now I'm looking to see what energy is involved with condensing. Well, there's no heat of condensing. So what is condensing the opposite of? It's the opposite of vaporizing. And we do have a heat of vaporization value, right? If we find it for benzene, so there's benzene's value, it's 30.8. So vaporizing, I'd have to put in 30.8 kilojoules. But if I'm condensing, that means 30.8 kilojoules needs to be released. That's why I put the negative there. And as you can see, that's going to make the two negatives cancel out, which is good. So the kilojoules is canceled out there. And now, I don't want to know moles of benzene. I want to know grams of benzene. So we need to figure out the molar mass there. So let's see. 12.01 times 6 plus the 6 hydrogens. The molar mass is about 78.12. Alright, so that'll make the moles cancel. And so let's figure out what that's going to be. Negative 2.45 times my molar mass of 78.12 and then divided by negative 30.8. With 3 sig figs, it looks like 6.21 grams. 6.21 grams of benzene would be my answer there. And once again, you have to put these negatives, okay? You may have said, well, what if I don't put the negatives? What if I put them both as positive? Then you would get marked wrong technically for your setup because you're not understanding the concept behind energy released and condensing, right? So you need to make sure you put those negatives there. Even though they cancel out, you need to make sure you put them there in the work so that way you get the full points. All right, that wraps up section 4. We've got one more section to go. We'll see you in the next video.